The space around you appears smooth and continuous, an empty stage where matter and energy perform the cosmic dance of existence. But if you could somehow magnify space itself by a factor of kc, zooming in beyond atoms, beyond quarks, beyond anything we can directly observe, you would discover that the fabric of spacetime is not smooth at all. Instead, it bubbles and froths like quantum champagne, with virtual particles popping into existence and annihilating themselves trillions upon trillions of times per second in every cubic centimeter of apparently empty space. This quantum foam represents the most fundamental texture of reality, a seething ocean of quantum fluctuations operating at the Planck scale, where distances become so small that the very concepts of space and time begin to break down. At scales of 10 to 35 meters and time scales of 10 to 43 seconds, spacetime itself becomes granular, pixelated, and certain, more like a turbulent quantum sea than the smooth geometric manifold described by Einstein. In general relativity, the discovery of quantum foam revolutionizes everything we think we know about the nature of empty space and the foundations of physical reality. What we call empty vacuum is actually the most energetically active substance in the universe, containing quantum fields that fluctuate with such violence that they could theoretically power entire civilizations if we could somehow harness their incredible energy density. Every cubic centimeter of space contains enough quantum vacuum energy to boil away Earth's oceans, yet this energy remains forever inaccessible to us, locked away by the fundamental quantum mechanical principles that create the foam structure itself. But here's what makes this absolutely mind-bending. Quantum foam suggests that at the deepest level, reality doesn't consist of particles moving through space and time. Instead, space and time themselves emerge from more fundamental quantum processes that operate according to principles we're only beginning to understand. The solid world around you, the flow of time you experience, even your own existence as a conscious observer, all of these might be emergent phenomena arising from quantum foam fluctuations operating at scales so small they make atoms look like galaxies. For over a century, physicists have been discovering that reality becomes increasingly strange and counterintuitive as we probe deeper into the foundations of existence. Quantum mechanics revealed that particles don't have definite properties until observed. Relativity showed that space and time are unified and dynamic rather than separate and absolute. But quantum foam takes these insights to their ultimate conclusion. At the Planck scale, the very concepts of space and time dissolve into quantum uncertainty, revealing a reality more bizarre than science fiction. Tonight, we're diving into the deepest level of physical reality that theoretical physics can currently explore. We'll discover how quantum mechanics and general relativity collide at the Planck scale to create quantum foam, why virtual particles constantly appear and disappear in apparently empty space, and how the bubbly structure of spacetime might hold keys to understanding the fundamental nature of existence itself. Along the way, we'll encounter 3 revelations that will transform your understanding of reality at its most fundamental level. First, that empty space is not empty at all but filled with quantum fields that fluctuate with such intensity they create a foam-like structure where virtual particles constantly materialize and dematerialize according to quantum uncertainty principles. Second, that spacetime geometry itself becomes uncertain at quantum scales, creating a regime where Einstein's smooth spacetime manifold breaks down into discrete, granular structures that operate according to quantum rather than classical principles. And third, that quantum foam might represent the fundamental substrate from which all physical phenomena emerge, including matter, energy, forces, space, and time themselves. The implications are staggering. If spacetime is fundamentally quantum foam, then everything you experience as solid, continuous, and deterministic might actually emerge from quantum processes operating at scales where causality, locality, and even existence itself become probabilistic rather than definite. Your experience of living in smooth spacetime might be analogous to experiencing the wetness of water without perceiving the underlying molecular motion that creates fluid properties. But this raises profound questions about the nature of reality and observation. If quantum foam operates at scales far beyond any possible experimental observation, how can we know it exists? What does it mean to talk about physical reality at scales where the concepts of measurement and observation break down completely? Are we approaching the ultimate limits of human knowledge about the physical universe? If you're ready to explore the quantum foundations of spacetime itself, subscribe and give this video a thumbs up. And here is something to contemplate as we begin. If reality is fundamentally quantum foam at the smallest scales, what does that suggest about the nature of consciousness and observation at quantum scales? Comment below with your thoughts. I'll pin the most thought-provoking response. This investigation will take us from the mathematical foundations of quantum field theory and general relativity through cutting-edge research in quantum gravity and string theory, to philosophical territories where the nature of spacetime meets the deepest questions about existence, observation, and the limits of human understanding about physical reality. Some discoveries we'll encounter might feel like they violate everything you think you know about space-time and physical existence. Others might feel like they reveal hidden truths about reality that you've intuited but couldn't articulate. All of them point toward a revolutionary understanding. The smooth, continuous spacetime we experience emerges from quantum foam processes operating at fundamental scales where classical concepts of physics break down completely. The universe doesn't just exist in spacetime. Spacetime itself emerges from quantum processes operating at scales where space and time become uncertain, granular, and fundamentally quantum mechanical. Quantum foam represents the deepest level of physical reality that current physics can explore, revealing spacetime as an emergent phenomenon rising from more fundamental quantum mechanical processes. Virtual particle dance in the quantum realm that underlies all physical reality. The most astonishing performance in the universe unfolds continuously. Virtual particles materialize out of pure quantum vacuum, live for impossibly brief moments, then annihilate back into nothingness, all while never violating any fundamental conservation laws. These ephemeral quantum dancers create what physicists call the quantum foam, the seething ocean of virtual particle activity that makes apparently empty space the most energetically active substance in the universe. Virtual particles aren't hypothetical constructs invented by physicists to explain mysterious phenomena. They are mathematical necessities that emerge directly from the fundamental principles of quantum mechanics combined with Einstein's special relativity. Heisenberg's uncertainty principle states that energy and time cannot both be precisely defined simultaneously, which means that quantum fields can borrow energy from the vacuum for brief periods to create particle-antiparticle pairs that must annihilate before the universe's energy accounting system detects the violation. The mathematics of quantum field theory reveals that virtual particle creation occurs everywhere throughout space at every moment, with the creation rate depending on the energy scale being probed. In every cubic centimeter of apparently empty space, virtual photons appear and disappear approximately 1,042 times per second. Virtual electron-positron pairs flash into existence at rates of 1,021 per second per cubic centimeter. Even virtual quarks and gluons contribute to the quantum foam through processes that require energies comparable to those found in particle accelerators. These virtual particle fluctuations aren't just theoretical predictions, they create measurable physical effects that have been confirmed through precision experiments. The Casimir effect demonstrates virtual particle reality through measurable forces between closely spaced metal plates that arise when virtual photons with certain wavelengths are excluded from the space between plates, creating imbalanced radiation pressure from virtual particles outside the plates compared to inside. Recent experiments have measured Casimir forces with extraordinary precision, confirming that virtual photons create real, measurable forces that match quantum field theory predictions to better than 1 part in 1,000. These measurements prove that virtual particles represent genuine physical phenomena, rather than mere mathematical artifacts, demonstrating that quantum foam has observable consequences despite operating at scales far below direct experimental access. The virtual particle dance operates according to quantum mechanical principles that seem to violate common sense about energy conservation and particle creation. Virtual particles can have any energy, including energies that would be impossible for real particles, because they exist for such brief periods that Heisenberg uncertainty prevents the universe from protecting conservation law violations during their fleeting existence. But virtual particles follow strict quantum mechanical rules that ensure overall conservation laws remain satisfied. Virtual particles must always appear in pairs that sum to zero energy and momentum. If a virtual photon carries positive energy, it must be balanced by another virtual photon carrying negative energy. Virtual particle-antiparticle pairs automatically satisfy charge conservation because particles and antiparticles have opposite charges that sum to zero. The quantum foam created by virtual particle activity exhibits fractal-like structure where smaller virtual particles appear within the quantum wakes of larger virtual particles, creating hierarchical virtual particle cascades that extend down to the Planck scale where quantum gravitational effects become important. This fractal foam structure means that quantum field fluctuations exhibit complexity at every scale of magnification, with finer structure revealed as we probe smaller distance scales. Computer simulations of quantum field theory on discrete spacetime lattices reveal the detailed structure of quantum foam at various energy scales. These lattice gauge theory calculations show that quantum foam exhibits universal statistical properties that don't depend on the specific types of virtual particles involved, suggesting that foam structure reflects fundamental features of quantum field theory itself rather than properties of particular particle types. Virtual particles mediate all fundamental forces in physics through quantum foam processes that connect distant objects through virtual particle exchange mechanisms. The electromagnetic force between charged particles operates through virtual photon exchange. The strong nuclear force binding quarks into protons and neutrons operates through virtual gluon exchange. Even gravity might operate through virtual graviton exchange. Though quantum gravitational effects remain beyond current experimental verification, this virtual particle force mediation means that all physical interactions occur through quantum foam processes that create temporary connections between distant objects through virtual particle bridges spanning the space between them. When you push against a wall, you are interacting with virtual photons in the quantum foam that mediate electromagnetic repulsion between electrons in your hand and electrons in the wall material. Recent theoretical work has revealed that virtual particle interactions can create quantum entanglement between distant objects through shared virtual particle exchanges that establish quantum correlations transcending classical spacetime separation. These virtual particle entanglement mechanisms might explain how quantum mechanical non-locality emerges from local quantum field interactions operating through quantum foam processes. The energy density of quantum foam approaches the Planck density, approximately 1094 grams per cubic centimeter, making virtual particle foam the most concentrated form of energy in the universe. This enormous energy density exceeds nuclear density by factors of 1077. Creating quantum foam energy concentrations that dwarf every other form of matter and energy while remaining completely inaccessible for technological exploitation. But quantum foam energy density creates theoretical problems for cosmology because Einstein's general relativity predicts that such enormous energy densities should curve spacetime so severely that the universe would collapse into a black hole immediately after the Big Bang. The cosmological constant problem represents one of the deepest unsolved problems in theoretical physics, explaining why quantum foam energy doesn't dominate cosmic evolution. Through gravitational effects, various theoretical approaches attempt to resolve the cosmological constant problem through mechanisms that cancel or neutralize quantum foam energy density. Supersymmetric theories predict that virtual particles and their supersymmetric partners contribute equal and opposite energy densities that cancel perfectly. Extra dimension theories suggest that quantum foam energy spreads across additional spatial dimensions rather than concentrating in our observed three-dimensional space. But quantum foam reveals something even deeper about the nature of physical reality. The distinction between real particles and virtual particles becomes arbitrary at fundamental scales, where quantum mechanics and relativity converge. All particles exhibit quantum mechanical properties that include virtual particle characteristics. Even electrons and photons spend time in virtual states during quantum interactions. The virtual particle dance demonstrates that the quantum vacuum represents the most fundamental state of physical reality rather than empty nothingness. Quantum fields cannot be turned off or removed. They represent permanent features of spacetime. that fluctuate continuously around minimum energy configurations that still contain infinite virtual particle activity. Recent developments in quantum field theory suggest that virtual particles might represent the fundamental building blocks from which all physical phenomena emerge. Through quantum condensation processes that organize virtual particle foam into stable patterns we recognize as matter, energy, and spacetime structure, reality at its deepest level might consist entirely of virtual particle interactions operating through quantum foam dynamics. The virtual particle dance operating throughout quantum foam reveals that empty space contains the most complex and energetically active processes in the universe, creating a quantum substrate that underlies all physical existence while remaining forever inaccessible to direct observation or technological exploitation. Virtual particles represent the universe's method for exploring quantum mechanical possibilities at every point in spacetime through continuous quantum foam activity. Planck scale geography. At the Planck scale, distances of approximately 1.6 times 10 to 35 meters and time intervals of 5.4 times 10 to 40 for seconds, the spacetime itself undergoes a phase transition more dramatic than anything in the observable universe. At these incomprehensibly small scales, the smooth geometric manifold described by Einstein's general relativity dissolves into quantum foam, where space and time become granular and certain and fundamentally probabilistic rather than continuous and deterministic. To comprehend the Planck scale, consider that a Planck length relates to the size of a proton the same way a proton relates to the size of the observable universe. If you could somehow magnify a Planck length to the size of a grain of sand, then a grain of sand would expand to fill a region larger than the Earth's orbit around the Sun. These scales are so small that they challenge the very concept of measurement and observation in any classical sense. The Planck scale emerges naturally from fundamental physical constants: the speed of light, Planck's constant from quantum mechanics, and Newton's gravitational constant from general relativity. When these three constants are combined to form natural units, they define characteristic scales where quantum mechanical effects and gravitational effects become equally important, creating a regime where neither quantum mechanics nor general relativity can be applied independently. At the Planck scale, quantum uncertainty principles become strong enough to affect spacetime geometry itself. Heisenberg uncertainty relations applied to gravitational fields predict that spacetime curvature fluctuates randomly with amplitudes comparable to the curvature itself, creating quantum gravitational noise that makes spacetime geometry fundamentally uncertain rather than smoothly defined. These quantum spacetime fluctuations create what physicist John Wheeler called spacetime foam, a quantum geometry where space and time break down into discrete probabilistic elements rather than continuous coordinates. Spacetime foam represents a quantum phase of geometry where classical concepts like distance, duration, and causal ordering become ill-defined due to quantum uncertainty effects operating at gravitational strength. Computer simulations of quantum spacetime attempt to model foam structure using discrete approaches that replace continuous spacetime with networks of quantum geometric relationships. Causal dynamical triangulation, loop quantum gravity, and spin foam models all predict that spacetime becomes granular at the Planck scale, with fundamental quantum geometric elements that cannot be subdivided further without losing physical meaning. The granular structure of quantum spacetime suggests that space and time are not infinitely divisible but have fundamental minimum units, quantum spacetime atoms that represent the smallest possible regions of existence. These spacetime quanta might be connected through quantum geometric relationships that create larger-scale spacetime structure, through quantum geometric phase transitions analogous to how molecular arrangements create matter. Phases. Planck scale geography includes quantum wormholes, microscopic connections between distant spacetime regions that appear and disappear through quantum fluctuations operating at scales where topology becomes uncertain. Virtual wormhole formation and annihilation might contribute to spacetime foam structure through quantum topology changes that alter spacetime connectivity at Planck scales, while remaining indetectable at macroscopic scales. Recent theoretical work suggests that Planck scale wormholes might enable non-local quantum mechanical correlations through spacetime, connections that transcend classical separation. Quantum entanglement between distant particles might operate through virtual wormhole networks in spacetime foam that create hidden spacetime connections between apparently separated quantum systems. The energy density fluctuations in spacetime foam approach the Planck density, energy density, at which gravitational effects become comparable to quantum mechanical effects. At Planck density, approximately 1094 grams per cubic centimeter, energy concentrations become so extreme that they create quantum black holes that appear and evaporate through Hawking radiation within. In Planck time intervals, virtual black hole formation and evaporation in spacetime foam might contribute to quantum gravitational noise that affects spacetime geometry through quantum mechanical processes operating at scales where general relativity breaks down. These virtual black holes represent quantum gravitational fluctuations that explore all possible spacetime configurations through quantum superposition processes operating across Planck scale geometries, but Planck scale geography faces fundamental measurement limitations because any attempt to probe Planck scale structure requires energies so enormous that they would create black holes larger than the regions being investigated. The Planck energy of approximately 1019 GeV exceeds the energy of cosmic ray particles by factors of millions, making direct experimental access to Planck scale physics impossible with any conceivable technology. This fundamental measurement limitation means that Planck scale physics must be explored through theoretical methods that extrapolate from lower energy phenomena where experiments remain possible. String theory, loop quantum gravity, and other quantum gravity approaches represent theoretical explorations of Planck scale geography using mathematical methods that transcend experimental limitation. Through theoretical consistency requirements, holographic principle approaches to quantum gravity suggest that Planck scale geography might be fundamentally two-dimensional rather than three-dimensional, with three-dimensional spacetime emerging as a holographic projection from quantum information processing on two-dimensional boundary surfaces. This holographic spacetime suggests that Planck scale geography operates according to information theoretic principles rather than geometric principles. The holographic nature of Planck scale geography could explain why spacetime foam exhibits information processing capabilities that enable quantum mechanical computations operating at scales where classical geometric concepts break down. Spacetime foam might represent quantum computational processes that create spacetime geometry through information processing rather than existing as fundamental geometric structure. Recent developments in quantum information theory suggest that spacetime geometry emerges from quantum entanglement patterns among fundamental quantum degrees of freedom operating at Planck scales. Spacetime connectivity might reflect quantum information sharing between Planck scale quantum systems rather than representing fundamental geometric relationships between spacetime points. This quantum informational approach to Planck scale geography suggests that spacetime foam represents distributed quantum computation operating across Planck scale networks that process quantum information through entanglement and quantum correlation mechanisms. Spacetime geometry emerges from quantum information processing rather than being fundamental to physical reality, but Planck scale geography also raises profound questions about the nature of existence and identity at fundamental scales. If spacetime becomes granular and uncertain at Planck scales, what constitutes individual identity for quantum systems operating across multiple Planck scale regions? Do particles have definite locations when spacetime location becomes quantum mechanically uncertain? The quantum geographic relationships operating at Planck scales might determine fundamental features of physical reality, including the dimensionality of space, the direction of time, and the strength of fundamental forces through boundary conditions that emerge from quantum geometric phase transitions operating during cosmic evolution. Planck scale geography might contain the blueprint for all macroscopic physical phenomena. Future theoretical developments in quantum gravity might reveal additional features of Planck scale geography, including quantum geometric phases, topological quantum transitions, and emergent dimensional structures that create macroscopic spacetime through quantum geometric condensation processes operating across cosmic evolution timescales. Planck scale geography represents the deepest frontier of theoretical physics. Planck scale geography demonstrates that spacetime itself has quantum mechanical structure that becomes apparent at energy scales where quantum mechanics and gravity converge to create quantum geometric phenomena. The smooth spacetime of general relativity emerges from underlying quantum geographic structure operating at Planck scales through quantum geometric processes that create classical spacetime as an emergent macroscopic phenomenon. Heisenberg's cosmic uncertainty. Werner Heisenberg's uncertainty principle, first formulated in 1927, extends far beyond the familiar limitations on measuring particle position and momentum at cosmic scales and quantum scales alike. Uncertainty principles create fundamental limits on how precisely any physical quantities can be defined simultaneously, leading to quantum fluctuations that make spacetime itself uncertain at the deepest levels of reality. The position-momentum uncertainty relation represents just one manifestation of a deeper principle that applies to any pair of quantum mechanical observables that do commute mathematically. Energy and time form another uncertainty pair, creating temporal quantum fluctuations that allow virtual particles to borrow energy from the quantum vacuum for brief periods without violating energy conservation, enabling the virtual particle activity that creates quantum foam structure. But Heisenberg uncertainty becomes truly cosmic when applied to gravitational fields and spacetime geometry. At the Planck scale, uncertainty in gravitational field measurements becomes comparable to the field strength itself, creating quantum gravitational fluctuations that make spacetime curvature fundamentally uncertain, rather than precisely definable according to Einstein's classical field equations. This gravitational uncertainty creates what physicists call metric fluctuations, random variations in spacetime geometry that occur because quantum mechanics prevents spacetime curvature from being precisely defined at arbitrarily small scales. These metric fluctuations contribute to spacetime foam structure by making geometric relationships between spacetime points fundamentally probabilistic rather than deterministic. Computer simulations of quantum gravity attempt to model these metric fluctuations by treating spacetime as a quantum field that fluctuates according to uncertainty principles. Loop quantum gravity calculations predict that spacetime area and volume become quantized at Planck scales, with fundamental minimum values that cannot be subdivided further due to quantum geometric uncertainty. NTI relations. The cosmic implications of Heisenberg uncertainty extend to cosmological scales through quantum fluctuations in the early universe that created the initial density perturbations responsible for all cosmic structure formation. Cosmic microwave background observations reveal quantum uncertainty fingerprints from the early universe that grew through gravitational amplification into galaxies, galaxy clusters, and the cosmic web we observe today. Inflation theory predicts that quantum vacuum fluctuations in scalar fields during the early universe were stretched to cosmic scales by exponential spacetime expansion, transforming microscopic quantum uncertainty into macroscopic cosmic structure. These inflated quantum fluctuations provide the only known mechanism for generating the initial conditions required for cosmic structure formation through gravitational collapse. Recent observations of cosmic microwave background polarization patterns provide direct evidence for these quantum uncertainty origins of cosmic structure. The statistical properties of temperature and polarization fluctuations match quantum field theory predictions for vacuum fluctuations that were amplified during cosmic inflation, confirming that cosmic structure emerges from fundamental quantum uncertainty processes. But Heisenberg uncertainty operates at every scale between quantum and cosmic, creating quantum noise that affects all physical processes through fundamental quantum mechanical limitations on measurement and prediction. Even macroscopic objects like pendulums and mechanical oscillators exhibit quantum uncertainty effects that limit the precision with which their position and momentum can be simultaneously defined. The quantum limit on mechanical system measurement precision has been achieved in laboratory experiments using laser interferometry to monitor mechanical oscillator motion with quantum limited precision. These experiments reveal quantum mechanical uncertainty affecting macroscopic objects, demonstrating that Heisenberg uncertainty represents fundamental physical limitations rather than limitations of measurement technology. Gravitational wave detectors like LIGO operate at quantum measurement limits, where Heisenberg uncertainty creates fundamental noise sources that limit detector sensitivity. Quantum uncertainty in photon number and phase creates shot noise and radiation pressure noise that together define quantum limits on gravitational wave detection sensitivity. That can only be overcome through quantum measurement enhancement techniques. Recent achievements in quantum-enhanced gravitational wave detection use quantum squeezing techniques to reduce uncertainty in one measurement variable at the expense of increased uncertainty in its conjugate variable, enabling detector sensitivities that surpass classical measurement limits through optimal distribution of quantum uncertainty according to Heisenberg principles. But cosmic uncertainty extends beyond measurement limitations to affect the fundamental nature of physical reality through quantum superposition effects that create multiple simultaneous possibilities for system evolution. Quantum systems don't have definite properties until observed, creating quantum uncertainty about physical reality itself rather than just measurement limitations about otherwise definite properties. This fundamental quantum uncertainty about physical reality becomes cosmically significant when applied to spacetime geometry and gravitational fields. Spacetime doesn't have definite curvature until observed through gravitational measurements, creating quantum geometric uncertainty that makes spacetime structure fundamentally probabilistic, rather than deterministic according to classical general relativity. Quantum cosmological models attempt to apply Heisenberg uncertainty to the universe as a whole, treating cosmic evolution as a quantum mechanical process where the universe exists in superposition states of different cosmic histories until observation collapses cosmic quantum uncertainty into definite cosmic evolution pathways. These quantum cosmologies predict that cosmic evolution involves fundamental quantum uncertainty about cosmic history itself. The many worlds interpretation of quantum mechanics suggests that cosmic quantum uncertainty creates multiple parallel universes that explore all possible cosmic evolution pathways simultaneously through quantum superposition effects operating at cosmic scales. Heisenberg uncertainty about cosmic evolution might reflect our limited observational access to infinite parallel cosmic histories rather than fundamental randomness in cosmic evolution. But recent developments in quantum information theory suggest that Heisenberg uncertainty might emerge from more fundamental information theoretic limitations on physical reality. Rather than representing irreducible quantum mechanical principles, information theoretic approaches to quantum mechanics propose that uncertainty principles reflect computational limitations on processing physical information rather than fundamental indeterminacy in physical reality itself. Quantum computational approaches to spacetime foam suggest that Heisenberg uncertainty emerges from computational complexity limitations in quantum gravitational calculations. Rather than representing fundamental quantum mechanical properties, spacetime foam might represent quantum computational processes operating at Planck scales where computational complexity creates apparent uncertainty through information processing limitations. This computational view of quantum uncertainty suggests that Heisenberg principles might represent fundamental limits on information processing in physical systems. Rather than fundamental indeterminacy in physical reality, quantum uncertainty might reflect computational complexity barriers that prevent physical systems from processing complete information about their own states and evolution. Future developments in quantum gravity and quantum information theory might reveal whether Heisenberg uncertainty represents fundamental quantum mechanical indeterminacy or emergent computational limitations in complex quantum systems. Understanding the fundamental nature of quantum uncertainty could revolutionize our comprehension of reality at quantum scales and cosmic scales. The cosmic significance of Heisenberg uncertainty extends from virtual particle creation and quantum foam through gravitational wave detection limitations to cosmic structure formation. From quantum vacuum fluctuations, uncertainty principles operate across every scale of physical reality, creating quantum limitations that affect phenomena spanning from Planck scale spacetime foam to cosmic scale structure formation T. Throughout the observable universe, Heisenberg uncertainty reveals that physical reality contains fundamental limitations on measurement, prediction, and even existence itself that transcend technological limitations and reflect deep quantum mechanical principles. These uncertainty principles create the quantum foam that makes spacetime bubbly at smallest scales while enabling cosmic structure formation through quantum fluctuation amplification. Across cosmic evolution, spacetime granularity, the smooth continuous spacetime of Einstein's general relativity, represents an approximation that breaks down catastrophically at the Planck scale, revealing that space and time are not infinitely divisible continua but consist of discrete quantum mechanical units that cannot be subdivided further without losing physical meaning. This spacetime granularity emerges when quantum mechanical principles are applied to gravitational fields, creating a regime where spacetime itself becomes pixelated, quantized, and fundamentally different from the geometric manifolds of classical physics. Spacetime granularity rises from the fundamental incompatibility between quantum mechanics and general relativity at extreme scales. Quantum mechanics predicts that all physical quantities have minimum measurable units determined by Planck's constant, while general relativity treats spacetime as smoothly continuous with arbitrarily fine geometric structure. At the Planck scale, these incompatible descriptions collide, forcing spacetime to become granular through quantum geometric processes. Loop quantum gravity, one of the leading approaches to quantum gravity, predicts that spacetime area and volume are quantized in discrete units proportional to the Planck area and Planck volume. These quantum geometric units represent the smallest possible regions of spacetime that can exist independently, creating spacetime atoms that form larger geometric structures through quantum superposition and quantum entanglement mechanisms. The mathematical framework of loop quantum gravity reveals that spacetime granularity emerges from quantum geometric operators that have discrete eigenvalue spectra rather than continuous ranges. Area operators measuring spacetime surface area can only return values that are integer multiples of fundamental area quanta, creating discrete spacetime geometry that contradicts classical assumptions about continuous geometric structure. Computer simulations of loop quantum gravity predict that spacetime granularity becomes apparent at scales approaching the Planck length, where smooth geometric relationships break down into discrete quantum geometric networks. These discrete spacetime networks exhibit complex connectivity patterns that create larger-scale geometric structure through collective quantum geometric phenomena. Analogous to how atomic arrangements create material properties, causal dynamical triangulation, another approach to quantum gravity, models spacetime granularity through discrete spacetime building blocks organized into simplicial complexes that approximate smooth spacetime geometry at large scales while exhibiting granular structure at small scales. These simulations reveal that granular spacetime can undergo geometric phase transitions that create different effective dimensionalities at different scales. The granular structure of spacetime suggests that concepts like distance and duration become discrete rather than continuous at fundamental scales. The minimum possible distance would be the Planck length, and the minimum possible time interval would be the Planck time, creating a granular spacetime lattice where geometric relationships are quantized according to quantum mechanical principles. This spacetime granularity has profound implications for particle physics and field theory. Quantum fields propagating through granular spacetime would experience discrete rather than continuous evolution, potentially creating modifications to quantum field theory that become apparent at high-energy scales where Planck scale effects might be detectable through precision measurements of particle interactions. Recent theoretical work suggests that spacetime granularity might create observable signatures in high-energy astrophysical phenomena where particles approach Planck scale energies. Ultra-high-energy cosmic rays and gamma rays from distant astronomical sources might exhibit subtle deviations from smooth spacetime propagation due to cumulative effects of spacetime granularity. Over cosmic distances, experimental searches for spacetime granularity effects include measurements of photon arrival times from distant gamma ray bursts to detect potential energy-dependent propagation delays that could indicate granular spacetime structure. While no definitive evidence for spacetime granularity has been detected, these experiments are pushing towards sensitivity levels where quantum gravitational effects might become observable. But spacetime granularity creates theoretical puzzles about the emergence of smooth classical spacetime from discrete quantum geometric foundations. How do quantum spacetime atoms combine to create the smooth geometric relationships observed in macroscopic spacetime? This emergence problem represents one of the deepest challenges in quantum gravity research. Coarse graining procedures in quantum gravity attempt to explain how smooth spacetime emerges from granular foundations through statistical averaging over large numbers of quantum spacetime units. Just as fluid mechanics emerges from molecular dynamics through statistical averaging, smooth spacetime geometry might emerge from quantum granular geometry through quantum statistical mechanics operating over quantum geometric degrees of freedom. Recent developments in holographic quantum gravity suggest that spacetime granularity might reflect information theoretic limitations rather than fundamental geometric properties. Holographic principle approaches propose that granular spacetime emerges from discrete quantum information processing on lower dimensional boundary surfaces, with spacetime granularity reflecting finite information processing capabilities rather than fundamental geometric discreteness. The emergent spacetime picture suggests that granularity represents a phase of quantum geometric organization rather than fundamental spacetime structure. Quantum geometric phase transitions might create regimes where spacetime appears granular at high energies but becomes smooth at lower energies, through quantum geometric condensation processes analogous to how matter undergoes phase transitions between discrete molecular arrangements and continuous fluid behavior. String theory approaches to spacetime granularity suggest that fundamental strings replace point particles and create extended geometric structure that smooths out spacetime granularity through string length scales that are comparable to Planck length scales. String interactions might create effective spacetime continuity through quantum string dynamics that average over discrete quantum geometric fluctuations. But spacetime granularity also raises fundamental questions about the nature of physical existence and identity at quantum geometric scales. If spacetime consists of discrete quantum geometric units, what determines their organization and connectivity of these units? Do spacetime atoms have internal structure, or do they represent truly elementary geometric entities? The quantum geometric relationships between spacetime atoms might determine fundamental features of physical reality, including the dimensionality of space, the direction of time, and the strength of fundamental forces. Spacetime granularity might contain encoding of all physical laws through quantum geometric boundary conditions that emerge from quantum geometric organization principles. Recent theoretical investigations explore whether spacetime granularity might be observer-dependent rather than representing fundamental physical structure. Different observers might perceive different effective spacetime granularities depending on their motion and gravitational environment, suggesting that granularity reflects measurement limitations rather than absolute geometric properties. Quantum reference frame approaches to spacetime granularity suggest that discrete quantum geometric structure might emerge from relational quantum geometric relationships. Rather than absolute spacetime discreteness, granular spacetime structure might reflect quantum geometric relationships between different physical systems rather than representing absolute spacetime properties independent of physical content. Future theoretical developments in quantum gravity might reveal whether spacetime granularity represents fundamental quantum geometric structure, or emergent phenomena arising from more fundamental quantum mechanical processes. Understanding the nature of spacetime granularity could revolutionize our comprehension of geometry, causality, and existence at the deepest physical scales. Spacetime granularity demonstrates that the smooth spacetime of classical physics emerges from underlying discrete quantum geometric structure operating at Planck scales where quantum mechanics and gravity converge to create quantum geometric phenomena. The continuous spacetime we experience represents a macroscopic approximation to fundamental quantum geometric discreteness that becomes apparent only at energy scales where quantum gravitational effects dominate classical geometric relationships. Energy density extremes. The quantum foam that permeates all of space contains energy densities so extreme they defy human comprehension and challenge our fundamental understanding of physical reality. Conservative estimates suggest that every cubic centimeter of apparently empty space contains enough quantum vacuum energy to power human civilization for billions of years, while more speculative calculations indicate energy densities that exceed nuclear energy by factors approaching 1077, making quantum foam the most energetically concentrated substance in the universe. These astronomical energy densities rise from virtual particle fluctuations that populate quantum foam with constant creation and annihilation of particle-antiparticle pairs. Across all possible energy scales, and like real particles that must satisfy energy conservation laws. Virtual particles can have any energy whatsoever because their brief existence times satisfy Heisenberg uncertainty relations that prevent the universe from detecting conservation law violations. During virtual particle lifetimes, quantum field theory calculations reveal that virtual particle contributions to vacuum energy density include terms from every possible virtual particle mass and energy, creating infinite sums that must be regulated using sophisticated mathematical techniques called renormalization, even after mathematical regularization. The remaining finite vacuum energy densities exceed observable cosmic energy densities by factors that create the infamous cosmological constant problem in theoretical physics. The vacuum energy density problem becomes apparent when quantum field theory predictions are compared with cosmological observations. If quantum foam really contains energy densities approaching the Planck density of keV grams per cubic centimeter, Einstein's general relativity predicts that such enormous energy concentrations should curve spacetime so severely that the entire universe would collapse into a black hole within Planck time intervals, contradicting the observed cosmic expansion and structure formation. Recent attempts to resolve the cosmological constant problem include supersymmetric theories that predict equal numbers of bosonic and fermionic virtual particles, with opposite sign contributions to vacuum energy density that cancel, precisely reducing total vacuum energy to zero or small values consistent with cosmological observations. However, experimental searches for supersymmetric particles have not yet confirmed supersymmetry at energy scales where it would resolve cosmological constant problems. Extra-dimensional approaches to vacuum energy suggest that quantum foam energy spreads across additional spatial dimensions rather than concentrating in the 3 dimensions we observe directly. String theory models with large extra dimensions predict that vacuum energy densities in our 3-dimensional space could be reduced by factors related to extra-dimensional volume, potentially explaining why observed vacuum energy densities are much smaller than quantum field theory predictions. But quantum foam energy densities create more than cosmological problems. They represent fundamental questions about the nature of energy and matter and existence itself. If empty space contains infinite energy densities, why can't this energy be extracted for technological purposes? What prevents quantum foam energy from manifesting as observable matter and radiation that would fundamentally alter cosmic evolution and structure formation? The answer involves quantum mechanical principles that make vacuum energy fundamentally inaccessible through classical energy extraction mechanisms. Vacuum energy represents the ground state energy of quantum fields that cannot be reduced further without violating quantum mechanical uncertainty principles. Attempting to extract energy from quantum vacuum would require creating regions of negative energy density that violate quantum inequalities in quantum field theory. Dynamic Casimir effect. Experiments represent the closest approaches to extracting energy from quantum vacuum fluctuations. By rapidly changing boundary conditions for electromagnetic fields, experimenters have succeeded in converting virtual photons into real photons that can be detected and measured, demonstrating that virtual particle energy can become real particle energy under specific dynamical conditions involving rapidly changing field configurations. Recent theoretical proposals for vacuum energy extraction include concepts like Casimir effect energy harvesting using rapidly oscillating conducting surfaces, quantum vacuum extraction using accelerated mirrors, and vacuum energy concentration using exotic matter configurations. While these proposals remain largely theoretical, they suggest that quantum foam energy might not be completely inaccessible under all possible technological configurations. The extreme energy densities in quantum foam create conditions that approach those found in the earliest moments of cosmic evolution, when the entire universe existed at energy densities comparable to quantum vacuum densities. Understanding quantum foam energy could provide insights into cosmic inflation, Big Bang nucleosynthesis, and other early universe phenomena where extreme energy densities determine cosmic evolutionary pathways. Inflation theory suggests that quantum vacuum energy in scalar fields might have driven exponential cosmic expansion during the early universe, converting vacuum energy into the matter and radiation that populate the cosmos today. This vacuum energy conversion represents the largest energy extraction from quantum foam in cosmic history, creating all observable matter and energy from quantum vacuum fluctuations. But quantum foam energy densities also operate at microscopic scales where virtual particle interactions create measurable effects in atomic and molecular physics. Quantum electrodynamic calculations of atomic energy levels include virtual photon contributions that modify electron binding energies by measurable amounts that have been confirmed through precision spectroscopic experiments. The Lamb shift in hydrogen atom energy levels represents one of the most precisely measured effects of quantum foam on atomic structure. Virtual photon interactions between electrons and protons create energy level modifications that deviate from simple column interaction predictions by amounts that match quantum electrodynamic calculations, including virtual particle corrections to better than 1 part in a billion. Recent developments in cavity quantum electrodynamics enable control and manipulation of virtual photon interactions through carefully designed electromagnetic cavity configurations that modify quantum foam properties in localized regions. These experiments demonstrate that quantum foam structure can be engineered and controlled, opening possibilities for quantum foam energy manipulation that could lead to technological applications. Quantum foam energy density calculations extend beyond electromagnetic virtual particles to include virtual particles from all fundamental interactions, including strong, weak, and gravitational forces. Virtual gluon contributions to quantum chromodynamic vacuum create color glass condensate states that affect nuclear physics and particle physics at energy scales where strong interactions dominate. Electromagnetic interactions. The QCD vacuum represents a complex quantum medium filled with virtual quark-antiquark pairs and virtual gluon interactions that create non-trivial vacuum structure affecting quark confinement, shear symmetry breaking, and other fundamental features of strong interaction physics. Understanding QCD vacuum structure could provide insights into nuclear physics and particle physics that transcend current theoretical capabilities. Future theoretical developments in quantum gravity might reveal whether quantum foam energy densities represent fundamental physical quantities or artifacts of incomplete theoretical understanding. About quantum field theory in curved spacetime. Quantum gravitational corrections to vacuum energy calculations could potentially resolve cosmological constant problems through gravitational effects that modify virtual particle contributions. Experimental approaches to measuring quantum foam energy densities include precision tests of gravitational effects from quantum vacuum, searches for vacuum energy modifications in strong electromagnetic fields, and attempts to detect gravitational signatures of virtual particle interactions. While direct measurement of total vacuum energy density remains impossible, indirect measurements of vacuum energy effects continue advancing experimental precision. The extreme energy densities in quantum foam represent both fundamental theoretical challenges and potential technological opportunities that could revolutionize energy production and spacetime manipulation if quantum foam energy extraction becomes technologically feasible. Understanding quantum foam energy could unlock energy resources that exceed all terrestrial energy sources by astronomical factors while providing insights into fundamental physics at energy scales W. Here, quantum mechanics and gravity converge to create quantum foam structure. Topology fluctuations at the quantum foam level of spacetime structure. Not only do space and time become granular and uncertain, but the very topology of spacetime, its connectivity and geometric relationships, undergoes constant fluctuations that create and destroy wormholes, change spatial connectivity, and alter the fundamental network structure that determines how different regions of space relate to each other. These topology fluctuations operate at scales so small that causality, locality, and even the notion of distinct spatial locations become quantum mechanically uncertain. Topology fluctuations emerge when quantum uncertainty principles are applied to spacetime geometry at the Planck scale, where quantum gravitational effects become strong enough to affect not just the curvature of spacetime, but its fundamental topological structure. just as virtual particles appear and disappear in quantum foam. Virtual spacetime connections can appear and disappear through quantum tunneling processes that temporarily connect distant spacetime regions through microscopic wormholes. John Wheeler's theoretical investigations in the 1950s first revealed that quantum mechanics applied to gravity predicts spacetime foam should exhibit multiply-connected topology, where distant spacetime points can be connected through quantum wormhole networks operating at Planck scales. These quantum wormholes would appear and evaporate so rapidly that they couldn't be observed directly but would contribute to spacetime foam structure through topological quantum fluctuations. Computer simulations of quantum gravity using causal dynamical triangulation reveal that spacetime topology does indeed fluctuate at small scales with simplicial complexes that model discrete spacetime geometry exhibiting constant topological changes as quantum transitions create and destroy connections between spacetime regions. These simulations confirm that topology fluctuations represent genuine quantum gravitational phenomena rather than mathematical artifacts. The physics of topology fluctuations operates through quantum tunneling processes that allow spacetime to tunnel between different topological configurations, according to quantum mechanical probability amplitudes. Just as quantum particles can tunnel through energy barriers in quantum mechanics, spacetime can tunnel between different topological arrangements through quantum gravitational processes operating at Planck scales. These quantum topology changes could have profound implications for quantum mechanics and information theory. If distant spacetime regions can be temporarily connected through virtual wormholes in quantum foam, quantum information might propagate through hidden spacetime channels that enable non-local quantum correlations through topological shortcuts rather than through mysterious spooky action at a distance mechanisms. Recent theoretical work on the R=EPR conjecture proposes that quantum entanglement between distant particles might operate through microscopic wormhole connections in spacetime foam that create hidden spacetime bridges between apparently separated quantum systems. These entanglement wormholes would provide physical mechanisms for quantum non-locality through topology fluctuations operating at quantum foam scales. Topology fluctuations also affect the fundamental nature of causality and information propagation in spacetime. If spacetime connectivity fluctuates quantum mechanically, then causal relationships between events might become uncertain rather than definite, creating quantum mechanical superposition states where cause-effect relationships exist in multiple possible configurations simultaneously until quantum measurement collapses topological uncertainty. The implications of fluctuating causality extend to fundamental questions about time travel and closed time-like curves. Topology fluctuations could temporarily create closed causal loops at quantum scales where effect precedes cause within microscopic spacetime regions, potentially enabling information transfer to the past through quantum foam processes operating below the threshold of classical causality restrictions. But topology fluctuations face severe constraints from quantum consistency requirements that prevent macroscopic causality violations through quantum mechanical protection mechanisms. The Novikov self-consistency principle and quantum coherence protection theorem suggest that quantum mechanics prevents topology fluctuations from creating paradoxes or inconsistencies in macroscopic spacetime through quantum interference effects that suppress problematic topological configurations. String theory approaches to topology fluctuations suggest that fundamental strings can mediate topological transitions through string interaction processes that change spacetime connectivity without violating quantum mechanical consistency requirements. String interactions might enable controlled topology fluctuations that could potentially be harnessed for exotic spacetime engineering applications in far future technologies. Loop quantum gravity predicts that topology fluctuations operate through quantum geometric transitions where discrete quantum spacetime units can reconnect in different configurations through quantum superposition states. These quantum geometric transitions could create temporary bridges between distant spacetime regions through quantum tunneling processes operating across networks of quantum spacetime atoms. The energy scales required for significant topology fluctuations approach the Planck energy, making direct experimental observation of topological quantum transitions impossible with any conceivable technology. However, cumulative effects of topology fluctuations might create subtle signatures in high precision. Experiments involving quantum mechanics, gravity, or spacetime geometry that could provide indirect evidence for quantum foam topological structure. Recent proposals for detecting topology fluctuation signatures include measurements of vacuum birefringence and strong magnetic field searches for anomalous quantum interference effects in precision, atomic physics experiments, and attempts to detect gravitational signatures of quantum foam topology through gravitational wave observations or tests of equivalence principle violations at quantum scales. Topology fluctuations might also affect fundamental constants and physical laws through quantum geometric processes that connect physical parameter values to spacetime topological structure. If physical constants reflect spacetime geometric properties, then topology fluctuations could create quantum mechanical uncertainty in fundamental constant values that might be detectable through precision measurement comparisons across cosmic distances and time intervals. The entropic implications of topology fluctuations raise questions about whether spacetime topological structure is fine-tuned for complex structure formation and biological evolution. If topology fluctuations determine cosmic evolution through their effects on fundamental constants and physical laws, then spacetime foam topological properties might represent entropic selection factors that enabled cosmic evolution toward complexity and consciousness. Quantum cosmological models that include topology fluctuations suggest that early universe evolution might have involved dramatic topological phase transitions that determine large-scale cosmic structure through quantum geometric processes operating during cosmic inflation. These topological cosmologies predict that cosmic evolution reflects underlying quantum foam topological dynamics scaled up to cosmic proportions. Future theoretical developments in quantum gravity might reveal whether topology fluctuations represent fundamental features of quantum spacetime or emergent phenomena arising from more fundamental quantum mechanical processes. Understanding quantum foam topology could revolutionize comprehension of spacetime structure, causality, and information propagation at quantum scales where classical spacetime concepts break down completely. Experimental quantum gravity research using analog spacetime systems attempts to simulate topology fluctuations in condensed matter systems where topological phase transitions can be controlled and observed directly. These analog gravity experiments could provide insights into quantum foam topological behavior through laboratory systems that exhibit similar mathematical structure to quantum gravitational topology fluctuations. The future possibility of spacetime engineering technologies based on controlled topology fluctuations could enable revolutionary transportation and communication capabilities that transcend current physical limitations through artificial wormhole creation, controlled causality modification, and exotic spacetime geometric manipulation operating through mastery of quantum foam topological dynamics. Topology fluctuations demonstrate that spacetime connectivity itself becomes quantum mechanical at Planck scales where quantum uncertainty affects not just spacetime curvature, but spacetime topological relationships. The fixed spacetime connectivity of classical physics emerges from underlying quantum topological dynamics operating through quantum foam processes that make spacetime network structure fundamentally uncertain and constantly fluctuating according to quantum mechanical principles. Observable consequences. While quantum foam operates at the inconceivably small Planck scale, far beyond any possible direct observation, its effects permeate upward through scales of physical reality to create measurable consequences that confirm the existence of this bizarre quantum spacetime structure. These observable quantum foam signatures range from precision atomic physics measurements to cosmic scale phenomena, revealing that the bubbly nature of spacetime at the smallest scales influences physical processes throughout the universe. The most precisely measured effect of quantum foam appears in quantum electrodynamic corrections to atomic energy levels, where virtual photon fluctuations in the electromagnetic quantum foam create small but precisely calculable shifts in electron binding energies. The Lamb shift in hydrogen, the difference between 2SV and 2P energy levels, results from virtual photon interactions that modify electron-proton electromagnetic binding through quantum foam Processes operating at atomic scales. Precision measurements of the Lamb shift match quantum electrodynamic calculations, including virtual photon corrections to extraordinary accuracy, better than 1 part in 10 for some transitions. These measurements provide direct experimental confirmation that virtual particles in electromagnetic quantum foam create real, measurable effects on atomic structure through mechanisms predicted by quantum field theory, calculations of vacuum polarization, and vertex corrections. The magnetic moment of the electron, measured to precision exceeding 1 part in 10, also reflects quantum foam contributions through virtual particle loops that modify electromagnetic interactions. Quantum electrodynamic calculations of electron magnetic moment anomalies include contributions from virtual photons, virtual electron-positron pairs, and virtual particles from all fundamental interactions, creating theoretical predictions that match experimental measurements with unprecedented precision. Casimir effect measurements provide the most direct experimental evidence for quantum foam energy density through measurable forces between conducting surfaces that arise from virtual photon pressure differences. When conducting plates are placed very close together, virtual photons with wavelengths longer than the plate separation cannot exist between the plates, creating radiation pressure imbalances from virtual photons outside versus inside the cavity that generate attractive forces proportional to quantum foam energy density. Recent Casimir effect experiments achieve precision measurements of virtual photon forces using micromechanical oscillators, atomic force microscopy, and optical interferometry techniques that can detect forces as small as 10 newtons. These measurements confirm quantum field theory predictions for virtual photon pressure and provide experimental verification that empty space contains real energy density from quantum foam. Fluctuations. Dynamic Casimir effect experiments demonstrate that quantum foam virtual particles can be converted into real particles through rapidly changing boundary conditions by oscillating conducting surfaces at frequencies approaching the resonant frequencies of virtual electromagnetic modes. Experimenters have succeeded in converting virtual photons into detectable real photons that can be measured spectroscopically, proving that virtual particles represent genuine physical entities rather than mathematical abstractions. The Hawking radiation predicted to emanate from black holes rises directly from quantum foam processes operating in curved spacetime near black hole horizons. Virtual particle pairs created in quantum foam can be separated by tidal forces near black hole event horizons, with one virtual particle falling into the black hole while its partner escapes to infinity as real Hawking radiation. This process converts black hole mass into thermal radiation through quantum foam virtual particle interactions, while Hawking radiation remains undetected from astronomical black holes due to extremely low temperatures. Analog Hawking radiation has been observed in laboratory systems including sonic black holes in Bose-Einstein condensates, optical black holes in nonlinear media, and hydrodynamic analogs in flowing water. These experiments confirm theoretical predictions about quantum foam behavior in accelerated reference frames and curved spacetime geometries. Cosmic microwave background observations reveal quantum foam signatures from the early universe where quantum vacuum fluctuations were amplified to cosmic scales during cosmic inflation. The statistical properties of CMB temperature and polarization anisotropies match theoretical predictions for quantum vacuum fluctuations that were stretched to astronomical scales by exponential spacetime expansion, providing observational evidence that cosmic structure originated from quantum foam processes. High-energy astrophysics phenomena might exhibit subtle signatures of quantum foam structure through cumulative effects over cosmic distances. Ultra-high-energy photons from distant gamma-ray bursts could experience small but potentially detectable modifications to propagation speeds if spacetime granularity creates energy-dependent dispersion relations that accumulate measurable effects over billion light-year propagation distances. Recent observations of gamma-ray bursts and blazars using Fermi Gamma-Ray Space Telescope and ground-based Cherenkov telescopes have placed stringent limits on spacetime granularity effects, constraining quantum gravity models that predict observable violations of Lorentz invariance at Planck scales. while no definitive quantum foam signatures have been detected. These observations approach sensitivity levels where quantum gravitational effects might become observable. Precision tests of fundamental physics principles provide additional opportunities for detecting quantum foam effects through high-precision measurements of physical constants, symmetries, and conservation laws that could be modified by quantum foam interactions. Tests of charge parity times symmetry, measurements of fundamental constant stability, and searches for equivalence principle violations all probe energy scales where quantum foam effects might create observable deviations from classical physics predictions. Gravitational wave astronomy opens new possibilities for detecting quantum foam signatures through precision measurements of spacetime curvature fluctuations. Quantum foam contributes to gravitational wave detector noise through fundamental quantum limits on measurement precision. But future detector technologies might achieve sensitivities where quantum foam spacetime fluctuations become directly observable as fundamental noise sources in gravitational wave measurements. The planned laser interferometer space antenna LISA will operate in space with reduced thermal and seismic noise, potentially enabling detection of quantum foam gravitational effects that remain below detection thresholds for ground-based detectors. Space-based gravitational wave detectors could probe quantum foam structure through measurements of spacetime fluctuations at sensitivity levels approaching fundamental quantum gravitational noise limits. Particle physics experiments at the highest available energies continue pushing toward energy scales where quantum foam effects might become directly observable through modifications to particle interaction cross-sections, scattering amplitudes, and decay processes, while current particle accelerators operate far below Planck scale energies. Precision measurements of standard model parameters continue improving sensitivity to potential quantum foam contributions to particle physics phenomena. Future particle physics experiments including proposed muon colliders, plasma wake field accelerators, and cosmic ray detection arrays might achieve energy scales or measurement precisions where quantum foam effects create observable signatures in particle interaction data. These experiments represent the closest approaches to directly probing quantum foam structure through controlled laboratory measurements. Quantum information experiments exploring fundamental limits on information processing and communication could reveal quantum foam effects through measurements of quantum channel capacities, decoherence rates, and entanglement dynamics that might be modified by quantum foam spacetime fluctuations. Quantum foam could create fundamental noise sources that affect quantum computation and quantum communication through spacetime uncertainty effects. Atomic clock networks distributed across cosmic baselines provide opportunities for detecting quantum foam effects through precision comparisons of time measurement accuracy that could reveal spacetime fluctuations affecting clock synchronization. Quantum foam temporal fluctuations might create correlated timing variations between distant atomic clocks that could be detected through network timing analysis. The convergence of multiple experimental approaches in atomic physics, astrophysics, gravitational waves, particle physics, and quantum information toward quantum foam detection capabilities suggests that observable quantum foam signatures might be discovered within decades through continued improvements in measurement precision and theoretical understanding of quantum foam observational consequences. Observable consequences of quantum foam demonstrate that the bizarre quantum spacetime structure operating at Planck scales creates measurable effects throughout physics that confirm theoretical predictions about virtual particles, spacetime uncertainty, and quantum gravitational phenomena. These observational confirmations provide experimental validation that spacetime really is bubbly at smallest scales through quantum foam processes, operating at the foundations of physical reality. At the deepest level, quantum foam might not represent fundamental spacetime structure at all, but rather the physical manifestation of information processing limitations in a universe that operates as a vast quantum computer. Recent developments in quantum information theory suggest that spacetime geometry, virtual particle fluctuations, and even the bubble-like structure of quantum foam emerge from more fundamental information theory. principles that govern how the universe processes, stores, and transmits quantum information. The holographic principle in quantum gravity proposes that all information contained within any volume of spacetime can be encoded on the boundary surface of that volume, suggesting that three-dimensional spacetime emerges from two-dimensional information processing. If spacetime is holographic, then quantum foam structure might reflect computational processes operating on boundary surfaces, rather than representing fundamental three-dimensional quantum geometric phenomena. This holographic perspective transforms quantum foam from a physical substance into an interface the way that two-dimensional quantum computation appears. When observed from within three-dimensional emergent spacetime, the bubbly structure of quantum foam might represent pixels in a cosmic display screen where underlying quantum computational processes create the appearance of three-dimensional spacetime through holographic projection mechanisms. String theory calculations reveal deep connections between quantum foam structure and information theory through the correspondence between string interactions and quantum computational processes. String loop diagrams that describe virtual particle interactions in quantum foam exhibit mathematical structures identical to quantum circuit diagrams that describe quantum computational algorithms, suggesting fundamental relationships between quantum foam physics and quantum information processing. Recent work on the ADS-CFT correspondence demonstrates explicit mathematical relationships between quantum gravity in the bulk spacetime and conformal field theory on boundary surfaces, providing concrete examples of how spacetime geometry emerges from quantum information processing. These correspondences suggest that quantum foam represents the holographic image of quantum computational processes rather than fundamental physical structure. Quantum error correction codes provide another connection between quantum foam and information theory. Just as quantum computers require error correction to maintain quantum coherence against environmental decoherence, spacetime might require quantum error correction mechanisms to maintain geometric coherence against quantum foam fluctuations that would otherwise destroy classical spacetime structure. Through quantum decoherence processes, the quantum error correction properties of holographic spacetime suggest that quantum foam fluctuations might represent quantum computational noise that gets corrected through holographic quantum error correction mechanisms operating across spacetime boundaries. Classical spacetime emerges through quantum error correction that suppresses quantum foam fluctuations below observable thresholds while preserving quantum information content. Computational complexity theory provides insights into quantum foam structure through investigations of computational resources required to simulate quantum field theory and quantum gravity. If spacetime operates as a quantum computer, then quantum foam might reflect computational complexity limitations in quantum gravitational calculations rather than representing fundamental physical indeterminacy. The computational complexity of simulating quantum foam using classical computers scales exponentially with system size, requiring computational resources that exceed the information processing capacity of the observable universe for even small quantum foam regions. This computational intractability suggests that quantum foam represents genuinely quantum computational phenomena that cannot be simulated efficiently using classical information processing. But quantum computational approaches to quantum foam simulation might achieve polynomial scaling through quantum algorithms that exploit quantum superposition and quantum entanglement to simulate quantum foam dynamics efficiently. These quantum simulation possibilities suggest that quantum foam might be fundamentally computational rather than representing traditional physical substance. Recent developments in tensor network approaches to quantum gravity provide computational tools for investigating information theoretic aspects of quantum foam structure. Tensor networks represent quantum states and quantum dynamics using network structures that naturally incorporate entanglement and information flow, enabling investigations of quantum foam information content and computational complexity. Tensor network calculations reveal that quantum foam exhibits information theoretic properties characteristic of highly entangled quantum systems with maximal information content and complex entanglement structure. These information theoretic features suggest that quantum foam represents quantum information processing at maximum computational capacity rather than representing simple physical fluctuations. The quantum information content of quantum foam approaches the Bekenstein bound, the maximum information content that can be contained within any spatial region without forming a black hole. This maximal information density suggests that quantum foam operates at fundamental information theoretic limits where further information compression would violate thermodynamic constraints on information processing. Quantum foam energy density calculations from information theory perspective suggest that virtual particle fluctuations might represent information processing costs rather than fundamental energy content. The enormous energy densities predicted for quantum foam might reflect computational energy requirements for processing maximal quantum information content rather than representing actual physical energy that could be extracted technologically. This information theoretic view of quantum foam energy could potentially resolve the cosmological constant problem by suggesting that quantum foam energy density represents computational overhead rather than gravitating energy density. Information processing energy might not contribute to spacetime curvature if it represents computational rather than physical energy content. Quantum entanglement between distant spacetime regions might operate through quantum foam information processing channels that enable non-local quantum correlations. Through distributed quantum computation across quantum foam networks, quantum foam might function as a quantum internet that enables quantum communication and quantum computation across spacetime. Through information theoretic mechanisms, recent investigations of quantum foam from quantum information perspective suggest that spacetime connectivity emerges from quantum entanglement patterns among quantum foam degrees of freedom. Rather than representing fundamental geometric relationships, spacetime geometry might be determined by quantum information sharing patterns that create geometric structure through information theoretic mechanisms. The emergence of causality from quantum information processing in quantum foam might explain how classical cause-effect relationships arise from quantum mechanical processes that don't respect classical causality constraints. Quantum foam information processing might create effective causality through quantum error correction and decoherence processes that suppress a causal quantum superposition states. Future developments in quantum information theory and quantum gravity might reveal whether quantum foam represents fundamental quantum mechanical phenomena or emergent computational processes arising from more fundamental information theoretic principles. Understanding quantum foam from information theoretic perspective could revolutionize comprehension of spacetime, matter, energy, and physical reality itself. Experimental quantum information approaches to investigating quantum foam include quantum simulation of quantum gravity using quantum computers, quantum communication experiments that probe spacetime information processing limits, and quantum sensing experiments that search for signatures of quantum foam information processing. Through precision measurements of quantum correlations and entanglement dynamics, the possibility that quantum foam represents universal quantum computation suggests that understanding quantum foam structure could enable revolutionary quantum computational technologies that harness spacetime information processing capabilities for quantum computing applications that transcend current technological limitations through direct interface with quantum foam. Computational resources. Quantum foam from information theory perspective reveals that the bubbly structure of spacetime at smallest scales might represent quantum computational processes rather than fundamental physical substance. The virtual particles, spacetime fluctuations, and quantum uncertainty that characterize quantum foam might emerge from information processing limitations and quantum computational dynamics operating at the foundation of physical reality. Through quantum information mechanisms, while cosmic expansion has reduced overall cosmic encounter rates, current cosmic epoch represents intermediate cosmic merger activity between early cosmic epochs with extremely high merger rates and future cosmic epochs with reduced merger activity due to cosmic expansion acceleration. Computer simulations of cosmic merger evolution across cosmic history reveal that merger mania peaked during intermediate cosmic epochs when cosmic structure formation had concentrated galaxies. into cosmic neighborhoods while cosmic expansion had not yet reduced encounter rates to current levels. Contemporary cosmic merger rates represent declining cosmic marriage activity compared to peak cosmic merger epochs. But merger mania faces evolutionary pressure from dark energy acceleration that will gradually reduce cosmic merger rates by expanding cosmic space and reducing gravitational encounter probabilities. Future cosmic merger activity will decline as cosmic expansion acceleration overcomes gravitational attraction and isolates cosmic communities from merger interactions. The cosmic future includes cosmic loneliness as accelerating expansion gradually isolates cosmic communities and ends the cosmic merger mania that has driven cosmic evolution. Throughout most of cosmic history, cosmic expansion acceleration represents cosmic divorce that will separate cosmic communities and end cosmic collaborative development through merger processes. Current observations suggest that we live during late-stage cosmic merger mania when cosmic marriages continue occurring while cosmic expansion acceleration begins reducing cosmic encounter rates. The present cosmic epoch represents transitional cosmic merger activity between peak cosmic marriage periods and future cosmic isolation periods. Merger mania demonstrates cosmic collaborative principles where cosmic development benefits from cosmic partnership through merger processes that combine cosmic resources and cosmic evolutionary achievements. Cosmic collaboration through galaxy mergers creates cosmic development opportunities that exceed individual cosmic evolutionary capabilities through cosmic teamwork operating across cosmic scales. Recent theoretical work suggests that merger mania might represent universal cosmic development principles where cosmic complexity emerges through collaborative cosmic development. Rather than individual cosmic evolution, cosmic merger processes might represent fundamental cosmic social organization that drives cosmic evolution toward increasing cosmic complexity through cosmic cooperation. The cosmic merger processes that will create Milkometa from our local group demonstrate cosmic collaborative development operating across cosmic time scales that span biological evolutionary history. These cosmic marriage processes connect current cosmic community development to future cosmic architectural achievements through cosmic collaborative engineering spanning cosmic time. Future observations will reveal merger mania operating across cosmic history with unprecedented detail, enabling cosmic marriage studies that trace collaborative cosmic development throughout cosmic collaborative history. These observations will test whether cosmic merger principles represent universal cosmic collaborative development or special cosmic social organization characteristics of current cosmic collaborative epoch. You exist within cosmic collaborative development that spans scales from local cosmic merger processes through cosmic neighborhood collaborative activities to cosmic web collaborative development that organizes cosmic evolution through merger mania operating across cosmic collaborative scales and cosmic collaborative time through gravitational marriage processes that create cosmic collaborative complexity approaching biological collaborative sophistication across cosmic space. Across the cosmic web, galaxies participate in social networks that span billions of light years, creating cosmic communities that exhibit communication patterns, resource sharing, and coordinated development processes that mirror biological social systems yet operate through purely gravitational mechanisms across scales that encompass substantial fractions of the observable universe. These cosmic social networks demonstrate that gravitational attraction creates more than mechanical assembly. It creates cosmic societies where gravitational interactions generate social complexity. Approaching biological social organization. The cosmic social networking that connects galactic communities operates through gravitational signals that propagate along dark matter filaments at the speed of light, enabling cosmic communication across cosmic web architecture spanning hundreds of millions of light years. When massive cosmic events occur, supernovae, galaxy mergers, active galactic nucleus outbursts, they create gravitational perturbations that travel throughout cosmic networks, influencing galactic evolution across vast cosmic social network scales. Our local group participates in cosmic social networks that connect our local galactic community to cosmic neighbors throughout the Virgo supercluster. Through gravitational communication channels operating across cosmic web infrastructure, the Cosmic flows that carry our local group toward massive cosmic attractors represent cosmic social networking that coordinates cosmic community development across cosmic social scales. Recent observations of coordinated star formation patterns across cosmic web filaments provide evidence for cosmic social networking operating across cosmic scales. Galaxy groups separated by hundreds of millions of light-years exhibit synchronized star formation episodes that suggest cosmic communication through gravitational signals propagating along dark matter highway networks connecting cosmic communities. Computer simulations of cosmic structure formation reveal that cosmic social networks emerge naturally from gravitational physics operating in expanding space filled with dark matter. Small cosmic communities develop gravitational connections to neighboring communities through dark matter filament networks, creating hierarchical cosmic social organization that spans scales from galaxy groups to cosmic superclusters. The cosmic web